Alright, so in this video we're going to look at this concept known as work. Okay, so work is a word that has two separate definitions in physics and the real world. So a lot of times what I do is I ask students, when you see this word work, what do you think of? And I often get, essentially, job, right? I get money a lot because money is associated with their job. But I also get, this idea that, you have to physically exert yourself. Right, and kind of that's the real world definition, but we can loosely use this as the physics definition in a way. Okay, so one thing to think about is the greater the force, right, or the greater the effort, right, that you have to put in. So this should be force. So the greater the force, the more effort you have to put in, right? So again, this goes back to this idea of physical exertion. And this will right now be kind of our working definition of work. So this is the one that we'll kind of build off of. So basically in the most simplest case, work is done when a force is applied to an object and the object moves, right, in the direction of the applied force. So what they like to do on multiple choice questions is they like to ask, is there work being done, or, is one of the, which of the cases is there work being done? And so the way to think about it is you have to meet three conditions for work to happen. And so the first one is there has to be a force. So you ask yourself, is there a force present? The second thing is there a change in motion? Okay, so if you say yes to force, you go to the motion question. And if you say yes to the motion question, then you go to the third question, is there has to be a cause. And the way the cause works is that this force has to cause that change in motion. And if at any point in time the answer to your question, and one of those three questions is no, then there's no work being done by that force. And we'll talk about that later, okay, how force is tied into all this. So the equation, or the symbol for work, is just simply W. The formula is F delta X. And the SI unit is joules. Sometimes you'll see a unit of Newton times meter. Okay, that's kind of the more official unit for work, but understanding that joules is actually a unit of energy, and we'll get the tie into work and energy here shortly. So the first thing, here are a couple of quick example problems. So we have an intern pushing a patient in gurney. They're producing an acceleration of 0.60 meters per second squared. And the question is, how much work does the intern do by pushing the patient in gurney through a distance of 2.5 meters? Now assume that the gurney moves without friction. If it moves with friction, then you have to account for that friction, and that's a little bit more advanced problem, which we'll talk about towards the end of this video. So we start with our equation. Work equals F delta X. Now notice though, they don't give us the force, but they give us enough information to calculate a force. Right? So they give us the mass, and then they give us the acceleration. So all I have to simply do is plug that equation of m times a into my work formula, so it becomes ma delta x. Now, they're talking about the patient and gurney, so the mass that we're accelerating is going to be the total mass of the patient and the gurney. And so it would be 72 plus 15 times our acceleration of 0.60, and it's going to move a distance of 2.5 meters. And so basically we're going to multiply 87 times 0.60 times 2.5 meters. And that's going to give us a work of 130 joules. You can also just simply calculate the force by doing 72 plus 15 times 0.60. Alright, this turns it into a two-step problem versus a one-step problem. It's just really personal preference of what you want to do. So the intern is exerting a force of 52.2 newtons, and that's what this value is right here. So if you did it as separate, this is the point where you plug in the 52.2. Alright, next question we have you're lifting a pumpkin from a pumpkin patch. You're going to lift, it's 3.2 kilograms, and you're going to lift at a height of 0.80 meters to check it out. How much work do you do in lifting the pumpkin from the ground? And so we have work equals F delta X. Now when you lift something, you have to lift with at minimum the weight of the object. Okay, so again, you can turn this into 2 steps, right? Or I can turn it into essentially a 1-step problem. But again, you're just going to do force times displacement. So I'm going to do mg delta x, or 3.2 times 10, and I'm lifting it 0.80 meters. And so I do that in my calculator, and I'm going to do 26 joules worth of work. Again, if you did 2 steps right at this point in time is where that 32 would go. Again, that's going to be personal preference of what you want to do. Now, as before, we talked about, what are some of the, ways work is done. So the main thing is that really if the object does not move, or really it should say does not change its motion, okay, then there is no work done on the object, right? So if the object, is undergoing a constant velocity, if it's just staying at rest, then there's going to be no work done on the object. Now, one thing is, that equation that we talked about before is just simply in a one-dimensional sense, but a lot of times forces don't act in one dimension. And so the way you have to think about it is when a force is exerted at an angle, only the component, right? So only the piece of the force that acts in the same direction of the displacement does the work. And so if I go over to this little diagram first, so if my motion is here to the right, that means the only piece that does any work on this object will be the x component, right? And so my delta x would be to the right, or if you want to say my delta x is horizontal, right? So a lot of times we talk about same direction. It doesn't necessarily mean they both have to be pointing in the positive x direction. It's just that they both have to be pointing horizontal. And so how does that change the formula? Well, it makes the formula F delta x cosine theta. And so this is now how you factor in that component piece. So we would know what the angle is that this force is being applied. So here's a quick example. Okay. So here is a quick example of talking about a lifeboat, a safety boat, being dropped into the water, right? And so it's sliding down a ramp and then continues to free fall. Suppose a 4,900 kilogram lifeboat slides down a distance of 5.0 meters on a ramp that makes an angle of 60 degrees with the vertical. How much work does gravity do on the boat? And so now we're just going to use that F delta x equation, right? And I know when we talked about inclined planes, we often used sine for the x direction, but understand that this is the piece that we're looking at is right here, and so that's actually going to be here, right? Or if I do it on my weight vector, right? So if I do it if I move that arrow up to where my weight is acting, right? It's this piece right here, where now that becomes our cosine. And so that's why it's going to be cosine of the angle instead of sine of the angle. And so we're going to do F will be our weight. So we can simplify this to be mg delta x cosine theta. And so we're going to do, it's a 4,900 kilogram boat. G is going to be 10. It's going to go 5 meters down the incline at an angle of 60 degrees. And so you plug all that into your calculator. And we get that gravity does 1.2 times 10 to the 5th joules worth of work. Okay, and so this is how that, when you bring the angle. So in general, anytime you see an angle involved, that's when you're going to use this cosine theta. And so really where this comes from is if you go to physics C, and if you're in calculus, it's what we call a dot product. And one way to solve dot products, dot products are a way of multiplying vectors, and we get a scalar answer in return. And so one way of determining dot product is using the magnitudes of the force, in this case the magnitude of the force and the magnitude of the displacement, and multiplying by the cosine of the angle. Now, since work is dependent on the cosine of the angle, right, and it's between the force and the displacement, right, we can now talk about how work can possess different types of, you can do different types of work. So you can do positive work, you can do negative work, or you can do zero work. Okay, and positive work is done when your angle between them is between 0 and 90. Okay, and so, I mean, if you want a quick little diagram, that would be, delta x this way, force up at an angle, right? And so that would be positive work. Negative work is now when you go past 90 all the way up to 180 degrees. So that would be, right, if my displacement is to the right and now my force is acting kind of like this. And so that would produce negative work. And one of the big forces that produces negative work is friction. And friction will act parallel to the motion, and so that would be at an angle of 180 degrees. Now notice that on these inequalities, I didn't put the equal to line underneath by 90. That's because to do zero work, your angle is going to be 90 degrees, right? And so that would be if I'm moving my object this way and I'm like pushing down on it, right? And so these are acting at right angles, and in fact the cosine of 90 is 0 degrees, or is not 0 degrees, right? It's 0. And so that just lets us know that if I have any forces acting perpendicular to the motion, then I'm going to have zero work done. And so here's a quick little ranking task, right? Remember, AP really likes these ranking tasks at this point in time. They're going to rank a lot of things. And so this one says to rank the cases in order of increasing work done by F from most negative to most positive. And all we really need to do is figure out, is the work positive, negative, or is there no work being done? So if I look at my first example, right, F and D are perpendicular. So for case A, there would be no work done, right, because there's a 90-degree angle. Okay. In case B, you would see that they're at 180 degrees towards each other, which makes this negative work. Okay, and it doesn't really necessarily mean what are the numbers. If you want to say it's negative FD, right? For case C, right, I have a non-zero angle, right? So theta does not equal 0, but it's positive. So maybe it's a better way to write that. We'll say that theta, right? So theta is less than 90, right? So it tells me I'm going to still do positive work, but it's going to be governed by that cosine formula. So this would be, right, FD cosine theta, which means it's going to be a lesser value, all right? And then if you look at the last one, theta is 0, so this is the full value of FD. And so if I'm going from most negative, I would have B, right, is less than A, which is less than C, which is less than D. Okay, you may also see it written as B is greater, or excuse me, D is greater than C, which is greater than A, which is greater than B. Right, these two are both the same answer. Okay, just note that how they're written with the inequality symbols. And so that's how you would rank these. Now, the next part here talks about when more than one force acts on an object, you can determine the net work, right? So the net work is simply the sum of the work done by each force separately. So remember, every force is doing work. And so that means that every force has an F times D factor to it, or F delta X cosine theta factor to it. And so the way to think about it is like net work is just simply W1 plus W2 plus dot dot dot, right? And so that just means it's going to be like F1 delta X, because the forces are going to move the same, or the object's going to move the same displacement. So you would F2 delta X plus dot dot dot, right? And so notice I didn't put the cosine in, but each one of these would essentially have a cosine part to it. But if I kind of now factor out that F, or that delta X, I say F1 plus F2 plus dot 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 delta X, the formula just essentially becomes the net force delta X, right? Because this F1 plus F2, right, is the sum of the forces. Okay, and so since individual amounts of work can be positive or negative, it is possible for the total work done on an object to be zero, right? Even though the individual amounts may be non-zero. Okay, so a lot of times when this situation happens, constant velocity, right? We're not accelerating, so A is equal to 0. But you would have a positive force doing work, then you would have negative friction doing work. If they're equal but opposite, they cancel out, so the net force would be 0, which means there's no work being done. So here's a quick example with that. It says, as your friends prepare to play Rock Hero, which is a combo of Rock Band and Guitar Hero, you push on the drum set to slide it into position. You exert a horizontal force of F of 24 newtons, and kinetic friction opposes the motion of the force of 22 newtons, or with a value of 22 newtons. You slide the drums a distance of 1.5 meters. The weight of the drum set is 54 newtons. What is the total work done on the drums? So sometimes when you do these problems, it may be helpful if you draw a free body diagram. So kind of the stuff we learned from Unit 2. Right? And so one thing you can notice from the free body diagram, if my motion is to the right, that automatically eliminates Fn and Fg from doing any work because they're now perpendicular to the motion. So to find the net work, or the total work done, I would just do the net force times delta X. Well, the net force is simply the applied force minus friction. And so I would do 24 minus 22 times 1.5 joules, or 1.5 meters, which gives me a work done of 3 joules. That's one way you can do it. You can also, kind of treat them separately. So I would say, okay, how much work does F do, right? Or capital F, the force I'm pushing with. And so the work done by capital F will just be 24 times 1.5, which is 36 joules. The work done by lowercase f, or friction, would be 22 times 1.5, which is 33 joules, right? Or it actually would be negative, right, because it's in the opposite direction. And then to find the net, all I simply do is add down. So it'd be work by my force over minus work done by friction. And so that's just going to be 3 joules. And so notice you get the same answer. Alright, so in the next video we're going to focus our efforts towards kinetic energy, and then we're going to talk about how is kinetic energy related to work, and then we'll move on to the different other forms of energy.